Alrighty, so we're going to take a look at the lateral displacement of a laser refracting through a piece of glass. We're going to derive an equation for the displacement using Snell's law, trig identities, and geometry. But before we get into the derivation, let's take a look at the setup we have here. As you can see, a laser is coming in at an angle. It hits the glass, and the laser seems to bend, and it comes out bending back to what it seems like parallel to the initial beam. So basically, we're going to find the distance d from the ruler to the displaced beam. So from the surface of the glass, the laser has an angle of incidence, and as it refracts, has an angle of refraction between the axis and the bended beam. To get a better picture of what's going on, let's jump right into the derivation.
Okay, so I just finished drawing a simplified diagram of the demonstration with all variables labeled. First thing we should know is that this piece of glass is a perfect rectangle. This means the sides are parallel, and that's crucial for us to know because that way we can solve for this d right here. Just to point out a few components, we have the angle of incidence of the laser beam when it reaches the glass. We have t, the thickness of glass, angle of refraction. We have angle phi, which is the angle between the initial beam and the refracted beam. L is the length of the beam inside the glass. And we have angles 3 and 4 as the beam leaves the glass. Because the rectangle is parallel, we can show that the initial laser beam extended with dotted lines is parallel with the beam after it's displaced. So this right here is parallel with that, and we can find d. To show that the laser beams are parallel, we must show that the angle of incidence right here is the same as angle 4 as the beam leaves the glass. This means we'll use Snell's law twice. Well, at the very surface, we see that Snell's law is n of air times angle of incidence equals to the n of glass times the angle of refraction. Well, now that we have this identified, we can see that angle of refraction is the same as the angle 3. And we know this because the axis, as you see in the diagram, they're parallel lines as well. So we use the geometry rule to show that angle r is equal to angle 3. Well, now that we established that angle 3 is the same angle as angle r, we use Snell's law at the bottom, and we have the n glass angle 3 equals n air angle 4. Well, it looks pretty much the same as the first Snell law that we did, so that establishes that angle 4 equals the incidence angle. So thus showing that the shift is parallel. Now we find for d. So displacement d can also be defined to be the small leg of the right triangle that we see right here. So that's the small leg of the triangle right here. There we go. Okay, and now we know using our knowledge of trig that to find d, we had the angle phi. So we set it up as sine phi equals the opposite d over the hypotenuse L. Then we just set d equals to L sine phi. Well, what is L? Well, we can find L by this triangle we have right here with the t acting as a long leg and the angle of the refraction. So t is the adjacent side of the angle r for cosine. So then we can use the trig identity cosine theta r equals adjacent t over the hypotenuse L. Then we set L equals to t over cosine theta r. Okay, so what is phi? This is an unknown angle. Well, we can use our geometry rule, as you can see right here, that the angle of incidence is equal to the angle of refraction plus the unknown angle of phi. So that way we can solve for phi to be the incidence angle minus the refraction angle. So now that we have all our components L, we have phi now. Now we just plug them into this equation right here to solve for d. Unfortunately, as I was recording this, I didn't see that it was cut off, so I'll just put a picture right here to show the final equation. D equals t over cosine theta r times sine the angle of incidence minus angle of refraction. Now let's check if this equation is accurate by doing a little quick experiment.
Okay, so what I'm doing here, I have the laser back on. I'm carefully tracing the path of the laser, and I'm marking the point of entry, the point of exit, as well as drawing the angle of refraction. Through this, I'll use a protractor to measure the angles and a ruler to measure the thickness of the glass. Then I'll plug those values into the derived equation and compare it to the actual measurement of D using a ruler. I'll fast forward this process and skip all the tracing and measuring. See you soon.
$2,000 later.
Alrighty, so I have here tracings of the glass and the path of the laser beam. Here we have the angle of incidence and the angle of refraction, and I also extended the initial beam with dotted lines here. We know that the index of refraction of air is 1. We don't know the index of refraction of glass, but we can solve for that using Snell's law. I measured the incidence angle to be 50 degrees, the refraction angle to be 30 degrees, and this helped me find the index of refraction of glass to be 1.5. So using our derived equation, we can plug in our values, and I measured the thickness to be 6 centimeters, and so I calculated D to be 2.37 centimeters. Measuring with the ruler, I got approximately 2.4 centimeters. So the percent discrepancy, the measured value minus the theoretical over the theoretical, I got approximately 1.28%.